Hey guys, I'm here back with another math video. Today we're going to be going over the inclusion, exclusion principle. It has its roots in set theory. I spelled principle wrong, but it has its roots in set theory. And it basically gives you a way that given a certain number of sets, for instance, let's say you have set A, set B, set C, and so on. It allows you to find the union of these sets, so and so on. It allows you to find that. So first of all, the union of set A and B by this principle happens to be A plus B, just adding the sets together, minus A intersection with B, and the intersection is just the number of elements that they share. So you add the elements of each set together and subtract the intersection. And that makes sense, right? Because with a union you don't want to count repeated elements in each set twice. So you have to, so if you count the elements of set A and B, you have to subtract the intersection between A and B because those elements are counted twice. In a union you don't want to count the elements that they share. You only want to count the elements that they share once. And by the inclusion-exclusion principle, this is also true. So A plus B plus C minus A intersection with B minus B intersection with C minus C intersection with A plus A intersection with B intersection with C. And if you look at this, it's a bit less intuitive, but if you count A, B, and C, the intersection between A and B was counted twice, the intersection between B and C were counted twice, the intersection of C and A was counted twice, so you subtract each of these. But when you subtract these, when you subtract the intersection between A and B, B and C and A, you subtract the intersection between A, B, and C one more time than is necessary. It's sort of hard to comprehend, but it'll probably be easier later when I give you a problem. So by this logic, you can actually generalize this. So the intersection between, the union between A, B, C, dot dot dot, to like X would be, let me think about this. I believe it would be A plus B plus C dot 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 plus X minus A intersection B minus B intersection C, and then all permutations of two numbers, so like all x choose two possible combinations of these, and then you add A, B with C, and all possible combinations of sets with 3. And you keep going until the last term is the intersection of all of them. You keep switching signs along the way. And that's basically like the general rule. Like you just keep switching signs and you always subtract or minus a combination of a certain number of intersection of sets. And I think it'll probably be easier if I sort of actually, why don't I actually, before I go into a problem, I'm going to put this in a set notation so it's actually easier to see. It might be easier for you to understand. I'm not on Paint because for some reason they upgraded Paint. I'm not entirely sure how to erase everything inside without using this thing. and the side is weird. Okay, that's good. Okay, so yeah, okay. So in set notation, that would sort of go like this. So A1 union A2 union A3 dot 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 all the way to union AP is equal to the summation of A from I to P, I guess, from AI minus the summation of I to P of oh yeah, I and I2, given that these aren't the same, of AI intersection of AI2, given that these aren't the same, and plus the intersection of I1, I2, I3 to P, different combinations of AI1, AI2, AI3, minus dot 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 dot, and keep switching signs until you have literally -1 times P to the P minus 1 of, because you switch the signs, right, of literally AI, like A1 union, intersection A2, intersection A3, all the way to AP. So that's in set notation, if you're the kind of person who likes set notation. And yeah, you can actually apply this to sets, but you can also, I can't erase this side, I'm sorry. You can apply this to sets, but you can also apply this to common like AMC 8 or AMC 10 problem, where they sort of give you like a Venn diagram. So let's say you just have sort of this, I'm just going to make this problem up. So you have a Venn diagram, and you took a survey of the class of dogs, cats, and birds, and you know that, let's say 30 people like dogs, 35 people like cats, and 40 people like birds totally. You know that let's say 10 people like dogs and cats, 15 people like cats and birds, and 20 people liked dogs and birds. Say that. And out of all of them, 5 people liked all 3. Okay. How many total people are there? So total people. Well, we can really just use the rule on this. So first we add all of the total people who like dogs, cats, and birds. So we add 30 plus 35 plus 40. Then we have to subtract the people who like dogs and cats, and subtract the people who both like dogs and birds, subtract the people who both like cats and birds. Right. So minus 10, minus 20, minus 15. Yeah, but so this is counted. So, but as you do that, you have to add the intersection of all 3, which is the people who like all dogs, cats, and birds. So you add 5, and this will give you the total people. So I just made this up. Hopefully it works. So it's 105 minus 45 plus 5. I think 65. I just made this question up. I hope I didn't make any calculation errors. I didn't screw anything up. But that's really how you use the inclusion-exclusion principle on easier problems, not just limited to set theory. Of course, it's also useful in set theory. Yeah. So that's it for today. Hope you learned about the inclusion-exclusion principle. I'll see you next week. Which is, cool and stuff, but let's see if we can simplify that down further. Now, one of the main problems with this expression is that we have